I want to start by introducing my organization, the Topos Institute. And we're a nonprofit institute aimed at social impact via socially conscious technology. And we've got these three pillars of work: collaborative modeling, collective intelligence, and research ethics. And I'm really just going to focus on this first one during this talk. We have a lot of projects that exemplify the principles that I'm going to show in this talk today. Though these are all really big projects, and what I really want to focus on is examples that can fit in a single slide that you really deeply understand so you can see the principles at work behind our technology. So I'm not going to be able to get into these kinds of big, important types of modeling, but I hope that if I want to get into just a few examples deeply, if something's not clear, definitely interrupt. I'd rather not just breeze through a bunch of examples. And before I start, I do want to make some tentative connections to AI safety as I understand it. I'm just going to make a lot of claims now, and I'm going to return to these slides at the end, and we can check whether or not you can cash out the checks that I'm writing. So to start with number one, there's this nice figure in Davidad's ARIA program, which is basically showing this game theoretic idea that there's a sort of race to the bottom of AI capabilities if we think that making actually verifiable, interpretable models is not economically feasible. So to the extent that we can show that these interpretable models are economically viable, that don't lose so much counterfactual economic output, we can reduce this incentive to hand over authority to uninterpretable black boxes. And I will argue that our compositional approach to modeling is uniquely poised to both handle large, complex models, which is required to capture that economic value, while also retaining the verifiability and interpretability. As a second point, I've got some examples of how I think it's understood that we don't want raw decisions to be the output of any kind of AI system. Rather, we want to have the target language be some sort of interpretable syntax and with a good semantics that we can interrogate. So, for example, in Davidad's ARIA proposal, we don't directly access the AI system. Rather, we interact with it via world models that it produces and that we can verify. And just looking at the past two talks at FAR, Anna gave a talk about moral decision making, where it's not just moral decisions are spat out, but rather there is this formal grammar with graphs and agents and outcomes, and that gives you a decision, but it also gives you this object that you can interpret and understand why the decision was that way. And lastly, Joshua gave a talk last week where he emphasized separating model from implementation, and that's precisely what category theory allows you to do in a very rigorous way. And lastly, I think on the topic of we want the AI to be aligned with our values, but there's always the question, whose values? And we understand that there needs to be some sort of collaborative dialogue between all various types of different stakeholders. And those stakeholders might have very different ways of seeing the world: a programmer versus a therapist versus an ecologist. We all have our different vocabularies of ways that we see the world and also talk about what's valuable or harmful. And I want to say that Topos is developing sophisticated notions of domain-specific languages that can be targeted for specific domain experts while retaining a kind of interoperability in a way that has a real rigor to it. So I think all three of these things are really important for AI safety, and I hope to show you that the kinds of techniques we're developing are actually helpful towards these ends. So those are the introductory notes, and now I want to get to the main portion of the talk, which is following this structure. And I'll also caveat that it's not really feasible to cover category theory at a technical level in such a short talk, and so I want to really focus on what can you do with it. So I'm hoping Python is a lingua franca for most people. I'll try to show Python examples and really contrast how would you do this in the old way of doing things and contrast that with how you can do it in the new way. So in this slide, I'm going to tell a sort of fictitious story about how once upon a time, programmers solved problems one at a time. You got a new problem, you wrote a new piece of code to solve it. And eventually we learned that this got really repetitive. And something magical happened, which is that we learned to use abstractions. So these have parameters, and for every input set of parameters, you can solve a different problem within some sort of class. And so these abstractions might be things like functions or data types or scripts that you run. And this is great. This makes life a lot easier if you've ever programmed. But to the extent that these problem classes seem similar, this again starts feeling repetitive. And if you sort of unfocus your eyes and you just see this whole problem class as itself a big problem, then you realize, well, we actually we have an isomorphic situation to the first thing. We're still just repeating ourselves whenever we hit something that's new and unforeseen. So I want to propose a vision for a future paradigm where we have the right language for talking about the structure of our new problem class and how it's related to our old one. And if we had the right language for talking about that, then in principle, we should be able to migrate our old abstraction and solve the new problem. And this would be true reuse of our abstractions. So I'm going to try to show at least 3 or 4 examples of moving from stage 2 to stage 3 throughout this talk. And so I'm going to make reference to 3 different types of abstractions, and I'll introduce them one at a time, but just to preview, one will be databases, and this is an example database schema. The next will be Petri nets, and those are basically bipartite graphs. And then lastly will be flowcharts. So here is an example of a database schema. And a database schema is an abstraction that allows you to codify certain logical constraints. So we say, oh, well, every edge has a source and a target vertex. Every vertex has a color. This is a language for talking about a certain type of thing. And on below, we have some example instances of this database. So we're trying to represent colored graphs. So this might be the colored graph we're talking about. If we were to represent this with a collection of tables like a database, we might say there's an edge table with 3 edges, and there's a vertex table with 3 vertices in these colors. We could also talk about a different representation of the same thing is this code, which itself generates the instance. But as I said, I don't want to use SQL, so I'm going to try to use Python for my examples. Here is a data type you could define in Python, which covers basically the same information. We're going to have this data structure, which has a set of vertices. We have a set of edges, which are just pairs of vertices, which are source and target. And then we have a dictionary that assigns each vertex a color. And on the right, I have how we would think about this in terms of Algebraic Julia, which is the software ecosystem that we develop at Topos. From that perspective, we actually want to be explicit about this schema we have. So we're going to actually encode this schema as an explicit object that we work with. So we have the objects, we have these foreign keys, which are called HOMs, we have this attribute type and this attribute. So this is all to say these are just 2 equivalent ways of talking about this data type that we're going to be working with. And I want to really contrast how we would do things ordinarily with a new paradigm of doing things. So let's start off with we have a function which creates this triangle. How does this work? Well, we start off with a graph. We add 3 vertices that are blue, red, and yellow. And then we add 3 edges, A to B, B to C, C to A. So this is our sort of building block. So what's our problem for abstraction reuse? Well, consider this big triangle. Of course, we could always write a function just like this for the big triangle, starting over from scratch again. But I think it's the hallmark that you've set things up in a good way that you can reuse this function to define this thing. Because if we look at it, we can see that this big triangle is nothing more than 3 of our original triangles. So how do we reuse this abstraction to solve our new problem? Well, I think if you were tasked with doing this, if this was your job to write code, I think you would be able to do something. And this is my attempt at doing this in a sort of ordinary coding style. One thing that we could do is modify our triangle function in a way that allows it to not just create new vertices, but actually reuse old existing vertices. So I'll add these optional parameters, our blue, our yellow, our red vertex. And basically, if you pass in an explicit number saying, I want to use this red vertex, it won't create a new one. And so we can do this refactor of this code, and then when our big triangle function, then it will be compositional. It will use our old abstraction. We create this triangle here, but we remember this is the blue vertex and this is the red vertex. Then we call the triangle function again, but reusing this blue vertex, so we make this bottom triangle. And then lastly, we call the triangle function again with this yellow and this red vertex. So nominally, we've addressed the concern, which was how do we reuse the old function to solve the new problem? But I think we paid a severe cost. We had to actually really do a hardcore refactor of our old implementation. And of course, at this small scale, it's possible, but you need to think at larger scales, this becomes really intractable. Also, we've changed the return type. It's no longer a graph because we actually need to know what are the vertices that came out of it. So that could break other code. So this is, I would say this is acceptable, but it's not satisfactory. Likewise, if we didn't want to change the triangle function at all, we could just create 3 triangles and then have some other sort of hacky code which is going to basically rewire. So that's going to create 3 disjoint triangles. And then we can basically rewire those edges to be pointing at the right things and then delete the extra vertices. Again, this is ugly. This is hard to maintain. And furthermore, it depends on knowing the exact implementation details of this triangle so that I know, what numbers to put in there. So this is all, I would say, very unsatisfactory and clunky. So I'm going to contrast this with our algebraic Julia approach adapted for Python, which is going to say, what's the process of doing this? Well, it's 3 steps. First, we declare our building blocks. Then we declare how those building blocks are related, and then we give that relation a certain semantics. In this case, we're going to give it the semantics of gluing things together. So let's start with this wiring diagram. So this is an undirected wiring diagram. There are these 3 big circles, which we call boxes, and these 3 dots, which we call junctions. And the semantics of this is to say, these junctions are ways of relating whatever goes into those boxes. And so we can create that wiring diagram with the code here, and then we can say, well, what goes into those boxes? And if we plug in these simple graphs into these boxes, we get something like this. And so what is the semantics that we're giving to this diagram? Well, we're saying, I want to glue things together. I want to glue the building blocks along their common interfaces. And you'll see that if we were to do that to this diagram, we will get the result we wanted. So this has a lot of important qualities to it. We didn't have to understand the implementation details of how triangle worked. We wrote something that was interpretable and legible because we just wrote this very declarative relation as opposed to a bunch of ugly imperative code. So I would say this is a solution for abstraction reuse for this one mini problem, which was how do I define big triangle in terms of little triangle? So next, I want to move on to Petri nets. These are a way of looking at bipartite graphs where I have 2 different vertex types. We've got species, which I'm going to represent with blue circles, and then we have transitions, which I'm going to represent with orange boxes. And then furthermore, we have inputs and outputs into these transitions, which basically we can think of this transition as a way of saying multiple inputs go to multiple outputs. If we were to represent this in a Python data structure, we might say, well, there's a set of strings, which is going to be these species. And then our transitions is going to associate other strings, like the inf and rec, with a list of inputs and a list of outputs. I don't think it's worth it to get into details, but there's a way of representing this exact same data with a relational database. So, but the idea is we can represent this type of data. And so what do we do with this data? This is really important for modeling, in particular epidemiology or logistics or chemistry. The idea is that we can think of there being populations living on these species, and these transitions are events that can happen. And when that event fires, it converts, let's say, a susceptible and infected person into 2 infected people. That's an infection transition. Likewise, there's a recovery transition, let's say, in this epidemiological model, which converts infected people to susceptible people. Yeah.
Are questions through it?
Yeah, questions are encouraged.
Great. All right. I'm going to ask a bunch of stupid ones.
Go ahead.
In general, I do that, and also specifically, I think I'm still having a hard time tracking the main advantage. I really like how you're comparing these side by side between the Python implementation and then the software Julia approach. Currently, I'm kind of following this as it's better at expressing compositions of relationships, like it's better at black boxing things, but I don't really understand why. And
I mean, I'll try to give some intuition for why it works. Certainly, goal 1 is showing that it works. And importantly, the abstractions that, this idea of gluing together a diagram like this can be made sense of in a very powerfully general kind of context. So this could be gluing together matrices to make a block matrix, or this could be, as you'll see, gluing together Petri nets, or it could be gluing together graphs. So the fact that we can write code that operates at this really general level in a way that doesn't depend on what I put into those boxes, that's a real paradigmatically different approach to writing code that makes sense for a particular function. I mean, it's somewhat similar to writing code for an interface, except that these interfaces that category theory is providing is actually really, they have some really nice properties. But yeah, maybe more examples will help. Any other questions? Yeah, I think maybe I should have stopped after this example and made sure that we appreciate that for this very toy problem that we were able to do something equivalent to writing this hacky code up here, but we did it in a declarative way that is, I would say, legible and compositional. Okay, so in this next example, we could again glue together Petri nets, but that would be boring. So I'm going to solve a different problem. Here we have this epidemiological model, SIS, and we can do a simulation with this Petri net. But what if the results aren't what we expected? And we say, oh, actually, there's a flaw in our way we are modeling this. It turns out there's not just a homogeneous group of susceptible people, but rather there's two different populations. There's the US people and the Europeans. And actually, we should model those as separate entities. So there's this distinction we failed to make. What we actually want is a Petri net with 4 species, where we have susceptible US, susceptible EU, infected US, infected EU, and we also want people to have the ability to move transcontinentally. So what's interesting is that we can talk about this kind of modeling thing that we're missing with its own Petri net. This is a Petri net that captures sort of this transportation dimension of US and EU. And so just like with spaces, we can multiply different dimensions together and get a multi-dimensional system. So as I will show in 2 slides, this is actually, in a very rigorous sense, the multiplication of these 2 Petri nets. But if we didn't have that insight and we actually just had to write some code in Python to actually say, OK, well, I had my old model. Now I realize I need to make this geographic distinction. What would I do? And this is going to be painful, but we have to go through it. Otherwise, we're not going to really fully appreciate what we're getting out of the declarative picture. So there's going to be some string hacking, because we don't want name collisions when we make our new Petri net. And there's going to be some for loops and some things that seem arbitrary. So if we had an arbitrary Petri net, here we have the SIS one, but if we had an arbitrary Petri net and we wanted to multiply it by this transportation model, what are we actually doing? Well, I might say for every single species in my Petri net, I want to create a US version and an EU version. And then furthermore, I want to add those transcontinental transitions between those 2 states I just added. Furthermore, for every transition in the original Petri net, I want to basically have a US copy of that transition and an EU copy of that transition. So here, this I gets turned into these 4 things. And this infection gets turned into this infection and that infection. So this was tedious and ugly. I mean, it's nice that we could do it in 18 lines of code, but still, this is not the type of thing you want to maintain. And furthermore, it's going to break the moment you change from Petri nets to something else. We want a solution that allows us to solve this problem, but for anything, not just for a specific data type, the kind of data type we're thinking of right at this moment in time. I'll skip this other solution. This involves multiplying 2 general Petri nets, but you get the point that there's string hacking, there's fragile code that's hard to maintain and is not really interpretable. So I want to really give you guys some intuition for why this is multiplication. And so I'm going to try to really dive into this 2 times 3 equals 6 example, because I think it's important. So what is the essence of 2 times 3 equals 6? Well, I think it's that we have a set of 2 things and a set of 3 things. Let's say we have some male dogs and some female dogs, and we want to take pairings of them. So we want pairings that draw from one of the sets and one from one of the other sets. And if we look at all the possible pairings here, we get 6 possible pairings. So I would say this is really the essence of what's going on with 2 times 3 equals 6. And so I want to just slightly generalize this and say, well, now let's say we have 2 kinds of things, cats and dogs. If we want to take pairs of these, it doesn't make sense in this very simple model to pair cats with dogs. And so we actually just want to pair the cats with the cats and the dogs with the dogs. So mathematically, we might say we have a tuple that gets multiplied by another tuple, and we just multiply them point-wise. First thing with the first thing, second thing with the second thing. So this is a slightly generalized notion of multiplication. Now, in my next slide, I'm going to show the exact same data on this slide, but in a slightly different way. So rather than talking about, I've got 2 cats and 1 cat and 2 dogs here, and 2 cats and 2 dogs here, I'm just going to have these abstract sets. There's Adam, Bob, and Alex. And I'm going to talk about what type of thing they are via a function into this other set, call it a set of types. So again, as complicated as this looks on the bottom, it's the exact same information as this. I've only, rather than talking about the internal structure of these sets, I'm representing that via a map into this set of types. So we can say if I multiply this whole thing, I get that thing. And this is really important, this perspective shift, to go from looking at the internal structure of something to looking at some external relationships. This is really, if we go back to the gluing example, what makes this so powerful is that I don't need to look what's inside these boxes. I'm talking about what it means to glue something purely via external relationships between things, not internal structure. That's really a key idea of what's making things general. So it goes the same for multiplication, that we can think of multiplying these sets via these external relationships, their maps into this set of types, is what allows us to encode the same information as this. And so by analogy, we won't get into the details, but if I want to multiply two Petri nets, all I need is a common base Petri net, a Petri net of types. So this says there's one type of species and there's two types of transitions. There's disease transitions, which are in green, and there's transportation transitions, which are in orange. And if we want to look at what transitions exist in the product, we best essentially look at all the pairings that we have. So there's two blues here and two blues there, which means we have 4 blues in the product. And we have 2 greens here and 2 greens here, and that's how we obtain these transitions. So again, we didn't need any of this code. All we had to do was declare a new Petri net, which relates the two that we were trying to multiply, and how those two Petri nets were related to the common base. So it's exactly, in a very rigorous way, dual to that gluing things together. And we are able to solve our problem with just a couple lines of code, which is purely declarative and, I want to say, interpretable. I'll also say that we have a lot of flexibility with this. So the difference between these two slides is that we realize some other modeling assumption. Well, what if people who are infected can't board planes and they're not actually going to travel from one place to the other? Well, we can actually capture that by saying, well, let's give this infection, the transportation of infectious people, and say, well, that's actually going to be a different color from these things. Suddenly, in our product, this disappears because I can't pair this up with anything. So suddenly we have this nice, very flexible modeling language for talking about multiplying things. By just changing one of those colors, we can, get that. So the last abstraction I want to talk about is flowcharts. And this is a kind of inspirational thing someone would draw on the whiteboard. And this, if you saw this on a whiteboard, you would not know what the people were doing when what they were trying to model. There are lots of different things that you could represent with this kind of wiring diagram. On the left, I have some sort of dynamical system. Maybe there's some traders who are trading things, and there's goods flowing in and goods flowing out. On the right-hand side, I have this sort of abstract mathematical relation that's like A plus B equals C, and the square root of C is B and D. And it's a completely different type of thing, but you could imagine that this is the square root. Box number 2 is the square root, and box 1 is addition. And so there's these two different semantics we could give to this same wiring diagram. And so what's our problem? Each time we've had a challenge problem. One was to glue things together. Another challenge was to make a distinction. The challenge problem here is we want to incorporate information at different levels of granularity. So we might say, well, actually, this box 1, I now know that there's actually more finer structure to that. It actually looks like this on the inside. So I want to substitute in somehow and obtain this new model. For both the dynamical system approach as well as the relation approach, we certainly can write code which does this substitution, but there's no way of getting around. You're just editing this function. You're manually going, you're changing these lines, you're trying to incorporate these new boxes and how they relate to the old things. This is, I would say, not a good solution. I'm going to just compare this to the algebraic Julia approach, which is where we actually explicitly in our code operate on these wiring diagrams as objects. And so I say, our initial model is taking wiring diagram 1, 2 and plugging in systems 1 and 2 into the boxes. But if I wanted this new model, then I say, OK, well, my new wiring diagram is substituting wiring diagram 3, 4 in for box 1. And now my new model is just simply substituting in systems 3, 4, and 2 into this new wiring diagram. And this is code that will work both for when your systems, your primitive systems, are these mathematical relations, but also if they're these dynamical systems. And so this is, again, a kind of declarative approach, which simultaneously is working at incredible levels of generality, where this kind of edit you made to fix the trading problem isn't going to help you make this kind of edit in the numerical problem. You've just edited some lines of source code and not in a way that was reusable in any way. So lastly, I want to mention we can change fluidly between these abstractions. So let's say you have some algorithm that only makes sense for graphs, like topological sort. But you have a Petri net, but you think morally you should be able to topologically sort a Petri net. Well, it turns out that we can, in a very declarative way, say, well, this is how you understand Petri nets as graphs. The inputs and outputs are kind of like edges, and the transition and species are kind of like vertices. That's simply all the data you ought morally declare in order to automatically be able to migrate these kinds of Petri nets into graphs, where we just sort of view these boxes as ordinary vertices. And this is precisely the kind of functionality that is really core to the algebraic Julia program. We call this a data migration. And the idea is that rather than writing code which converts Petri nets to graphs, you simply declare what is the relationship between a Petri net and a graph at a high level. And everything else should just come automatically, and it does. Likewise, we could move information back the other way. So let's say we're trying to model some sort of transition system that has things with one input and one output. So we use a graph, because a graph is a great language for talking about that. But later in life, we learn, oh, there's actually these transitions that have multiple inputs and multiple outputs. I didn't realize I needed that, and I've written my entire code base to work with graphs and not Petri nets. How do we change our assumption and reuse our old work without writing everything from scratch? Well, again, we can do a data migration which interprets edges as one input, one output transitions. And the idea is that the way that algebraic Julia is set up, you should be able to migrate all of your old code in a way that allows you to transport all of your old work into the new assumption, which is that, okay, well, now I want to allow this sort of thing. And so, again, here's some hacky Python code which will do these transformations. You could always write this. There's always a hacky way to do something. But the question is, okay, well, this helps you with the specific problem. It does not help you with any other problem. The moment graphs change slightly or Petri nets change slightly, this code will break. This is tedious, hard to debug, gets in the way of our true understanding of what's going on. And we should just compare this with the one-line algebraic Julia solution, which is, okay, I've got this relationship between Petri nets and graphs. Now I just want to do either, I want to give that relationship the semantics of a sigma migration, which moves things forward. So this was a this was a sigma migration because the arrow is pointing that way, and I was able to push instances forward. This was a delta migration, where I have a mapping this way, and I'm able to pull things back. So there's a rich language for moving information between these different perspectives. And I want to say what this is doing is allowing you to incorporate new assumptions, such as there are multiple inputs and outputs. Yeah.
Could you explain again the difference between a sigma and a delta migration? Why
Yeah.
are they not just the same migration?
Yeah. So I think that's a technical question. But yeah, practically, there are ways of defining these mappings between the two schemas that have an orientation. So I'm assigning things over here to things over there. Sigma migrations allow you to push things forward, push instances forward along that mapping, whereas delta migrations pull information back along that mapping. So they're different things. They're related in important ways. But this is just to say that it's not like there's a unique way to canonically move information from one perspective to another. In category theory has lots of abstractions for that they understand well how they relate to each other and what they are. So now I have a summary slide. The common theme here is that we want to be declaring relationships between things rather than just plain writing code. And I think that there's some really important things that really capture this notion of legibility and corrigibility, which is we want to be able to glue different perspectives together. We want the ability we have done something and then we realize, oh, I should have made a distinction. We want to be able to incorporate information at different levels of granularity. And lastly, we want to be able to make a new assumption and move all of our old ways of doing things into the new way of seeing things in a very natural way that preserves what we were trying to say. And I think that in each of these cases, there's a hacky way to do that that doesn't generalize, and there's also a category theoretic method. And so there's these technical words that you can definitely look into if you're curious. This gluing together things is called colimits. These multiplying things or making distinctions are limits. This hierarchical integration is based on operads, and these things called data migrations allow us to move from one perspective to another. So now let's come back to, is this relevant to AI safety? Well, I want to say that these tools that we've been building are actually allowing us to build very complicated models from simpler building blocks in a way that doesn't become this entire spaghetti mess of code. We have these well-understood relationships between syntax and semantics and relationships between them, such as these data migrations. And I want to say that, especially that data migration story of having people in different perspectives being able to migrate their perspectives into each other's languages in ways that preserve what they mean. So I also have some slides about why this works. I guess I have time to talk about it. So again, I'm not going to give a technical category theory talk because I don't think there's time, but I want to provide some intuition for even non-technical people to have some reason to believe why this branch of abstract math could actually be useful for building software. So the only definition in this talk is going to be that a category is a bunch of things that are related to each other. That might just be a bunch of dots and arrows right there. Maybe we give those arrows names. Here, we actually say, well, our dots are going to be sets of things, and these arrows are going to be functions. So these are all set theoretic functions, where a function assigns for every element in the domain an element of the codomain. So these are all categories. And I think the key intuition I want to communicate today is that category theory is concerned with universal properties. And a universal property is a way of thinking of something that you once thought was a property of some object, and then a perspective change and seeing that as a relationship that that object has to other objects. So I'm going to talk about a very specific example of a universal property. So let's consider emptiness. So if you ask someone on the street, what is the empty set? How do you define the empty set? They will tell you it's the set that doesn't have anything in it. And that's perfectly good definition. I understand why someone would give it. But I want to say it's not the right definition, because as soon as we start trying to talk about other empty things, such as empty graphs or empty matrices or empty dynamical systems, this definition doesn't help us at all. A better definition would be that the empty set is the unique set which has exactly one function into every other set. So if you look here in the diagram, you can see that because a function assigns an element of the codomain for every element of the domain, that there's, as soon as you have a single element, there's suddenly multiple functions that you might have into another set. The empty set is the only one which there's only one way to give a function, which is an empty function. So it might seem unusual. This might seem like an unusual definition. It seems like an odd quirk of the empty set rather than the defining trait of it. But I want to say that the moment we start looking at other types of empty systems, that we realize this is the definition that generalizes, this is not. So if we have graphs, let's say, here we have our colored graphs from the beginning, we might say, okay, well, what is an empty graph? Well, now a graph has these two sets, vertices and edges. And we might say, okay, well, the empty graph is the one that has no vertices nor edges. But if we look at this context of graphs and graph morphisms, which are the basically fundamental way of relating graphs to each other, then we'll also notice that the empty graph is the unique graph, which has exactly one graph morphism into every other graph. And so maybe you'll just have to take it on faith that this is the definition that really generalizes and is incredibly powerful. And note, the reason why it generalizes is that the definition of this does not require me to look inside any particular graph. I only need to talk about how graphs are related to each other or how sets are related to each other. So the moral here is that category theory enforces good conceptual hygiene. It's forcing you to not allow yourself to depend on, quote, implementation details of the things that feature in your definitions. And this is really what's underlying the ability for us to build models that can be extended and generalized. And everything in that table, all those virtues we had of drawing distinctions or gluing together in a way that's very generic, comes from this, ultimately. So for my last slide, I want to say that category theory is useful. We have these things that are generalized notions of all these really interesting and deep concepts like multiplication or gluing things together. Things I didn't get to talk about are basically finding and replacing patterns, or open systems versus closed systems, and symmetries. There's all sorts of things that we can talk about using universal properties, which I think is really, really impressive, because it's not easy, it's not easy to come up with this definition. So there's a lot of category theorists who've done a lot of work to try to capture important concepts via these properties. But once you get something like this, you get a really powerful tool. And these abstractions all fit nicely with each other. It's not like you made a bunch of abstractions out of functions and data types and code and scripts, and then eventually you start getting this house of cards that's ready to collapse at any point in time. No, this all fits together in a nice cohesive story. In general, we're replacing code with high-level data, and this is what allows us to migrate that data in a way that when we have a new problem class, we understand our algorithm in a way that allows us to update it. So I hope I provided quite a few examples of this. And yeah, that's all I want to say. So thank you.